Lugares são como pessoas. Tem aqueles que apenas passam por nossa vida e aqueles que deixam a sua marca. Tem aqueles sem graça e aqueles instigantes. Lugares são como pessoas. Tem lugar que tem um incrível poder de dar um clique na nossa alma e quando a gente vê, já entrou no nosso coração e ele está ali, instalado. Salvador é assim. Uma festa para os sentidos. O gosto do dendê fica na boca, quase como uma tatuagem no paladar. O cheiro do mar não se contenta em ser sentido. O sal gruda no corpo e quer se misturar com o nosso suor. As imagens são tão carregadas de sentido que parecem ter sempre algo novo para lhe mostrar, mesmo que você já tenha visto dezenas de vezes. E a batida? Será que é por acaso que tem o mesmo nome daquilo que lá no peito faz a gente se sentir vivo? Uma cidade que é dividida em duas partes e ligada por um elevador não nasceu mesmo para ser convencional. Aqui, o palco anda. E o mais impressionante, o povo sai andando atrás. Aqui o banho pode ser de mar, mas se preferir, pode ser de pipoca também. É o coração da África, o berço do Brasil e tem o sorriso que é do tamanho do mundo. Só quem nasceu de uma mistura pode juntar tão bem coisas tão diferentes. Salvador tem um santo do candomblé para cada dia da semana e uma igreja para cada dia do ano. Salvador é superlativa, generosa, bem-humorada e de bem com a vida. Não dá para ser o mesmo depois de conhecê-la. Não dá para ser igual depois de sentir suas sensações. Não dá para ser igual depois de perceber suas singularidades. Não dá para ser igual depois de sentir seus cheiros, ouvir seus sons, provar seus sabores. Não dá para ser igual depois de ouvir suas histórias. Não dá para ser igual depois de conhecer um lugar tão surpreendentemente diferente. Salvador, você sente que é diferente.
Ladies and gentlemen, welcome, good morning, good afternoon, and good evening, depending on where you are. Ladies and gentlemen, this fourth conference on statistics and data science has been organized in collaboration with the Federal University of Bahia. Its purpose is to bring together researchers and practitioners from the academy and from the industry that develop and apply statistical and computational methods for data science. This conference will provide an environment to share and discuss ways to improve access to knowledge and promote interdisciplinary collaborations. The scientific program will be very appealing for most statisticians and data scientists interested in quantitative methods for decision-making and will include plenary talks, short courses, roundtables, and contributed posters. Together with the fourth conference on statistics and data science, the final project of the second class of the specialization of data science and big data of the Federal University of Bahia will be presented and discussed. You can find the links for all sessions and all posters on the conference website. We would like to thank all the local, national, and international institutions that endorsed and supported this conference and helped making the organization of this event possible. The Federal University of Bahia, the specialization in data science and big data from the Federal University of Bahia. CONV3, o Conselho Regional de Estatística da Terceira Região. ABE, Brazilian Statistical Association. RBRAS, Brazilian Region of the International Biometric Society. ISI, the International Statistical Institute, the Special Interest Group on Data Science from the International Statistical Institute, the International Society for Business and Industrial Statistics, the International Association for Statistical Computing, and the ASA, the American Statistical Association. We are also grateful to our national and international guests who participate as plenary speaker, speakers, short course presenters, discussants in roundtables, and presenters for contributed posters, and of course, to you all participants. We'll now compose the opening table. And for that, we invite Professor Lisandra Fábio, Chair of the Local Organizing Committee of the CSDS 2022. Professor Evandro Santos, Dean of the Institute of Mathematics and Statistics of the Federal University of Bahia. Professor Olivia Maria Cordeiro de Oliveira, Research Coordinator of the Dean's Office for Research and Postgraduate Studies of the Federal University of Bahia on behalf of the Rector. And Professor Paulo Canas Rodrigues, Head of the Department of Statistics of the Federal University of Bahia and Chair of the Scientific Program Committee of the CSDS 2022. I would like now to invite everybody to listen to the national anthem, which will be sung by the singer Raíza Soares.
Ouvira do Ipiranga, em margens plácidas, de povo herói com brado retumbante, e o sol da liberdade em raios fúlgidos brilhou no céu da pátria nesse instante. Seu penhor dessa igualdade conseguimos conquistar com braço forte. Em teu seio, ó liberdade, desafia o nosso peito a própria morte. Ó pátria amada, idolatrada, salve, salve. Brasil, de um sonho intenso, um raio vívido, de amor e de esperança, a terra desce. Sem teu formoso céu, risonho e límpido, a imagem do cruzeiro resplandece. Gigante pela própria natureza, és bela, és forte, impávido colosso. Se o teu futuro espelha essa grandeza, terra dourada, entre outras mil, és tu, Brasil, ó pátria amada, dos filhos deste sol és mãe, gentil, pátria amada, Brasil.
Thank you very much, Raíza Soares. Now, I would like to welcome you. We will hear from the chair of the local organizing committee of the 4th Conference on Statistics and Data Science, Professor Lisandra Fábio.
Good morning. Firstly, I would like to express my gratitude to the present authorities for accepting our invitation to participate in this opening ceremony. And on the behalf of the local organizing committee, I would like to welcome all of you to the 4th Conference on Statistics and Data Science in a virtual format.
I believe that we're having some technical problems right now, so I'll pass the word over to Professor Evandro Santos, the Dean of the Institute of Mathematics and Statistics of the Federal University of Bahia, and later we'll come back to Lisandra Castilho Fábio.
Bom dia a todos. É mais uma vez um encontro, um congresso de ciência de dados, estatística. Esse evento que cresceu muito, né? Paulo estava falando, eu lembro bem da primeira edição. Primeira e segunda edições foram presenciais e por força da pandemia tivemos as duas últimas, incluindo essa, remotas, mas o evento não perdeu em nada de brilho, muito pelo contrário, o evento cresceu. Se na primeira edição tivemos muita gente do Brasil e poucas pessoas da Europa, dos Estados Unidos, nas edições seguintes esse número só cresceu, tanto nos participantes brasileiros como nos participantes internacionais, atingindo mais países, né? E a cada ano esse evento cresce exponencialmente, e isso com certeza traz uma grande energia para os projetos que o departamento tem tocado, especialmente projetos recentes, que eu tenho certeza teremos em breve boas notícias, né? Notícias positivas. E quero desejar a todos um grande evento, aproveitem bastante o evento, tem muitas palestras, muitas mesas, todas elas de grande valia, com grandes pesquisadores, trazendo inovações, trazendo novas ideias, e um congresso com essa característica sempre é um bom momento para trocar novas ideias, aprender novas coisas e abrilhantar cada vez mais a pesquisa. Parabéns, Alexandra, parabéns a Paulo, né? Parabéns ao Departamento de Estatística, parabéns ao Instituto, parabéns à UFBA, porque realizar eventos dessa magnitude em tempos, vamos dizer assim, nos nossos tempos hoje, né? Nossos tempos em que nós temos dificuldades com verbas, com uma série de coisas, é realmente um ato de bravura e mostra que a universidade está viva e vai continuar viva. Parabéns, Paulo, parabéns a todos e aproveitem o evento. Um grande abraço a todos.
Thank you, Evandro. And now I'll word over to Professor Lisandra Fábio.
Hi, everyone. I had a little technical problem. I'm sorry. I will start again my talk. And good morning. Firstly, I'd like to express my gratitude to the present authorities for accepting our invitation to participate in this opening ceremony. And on the behalf of the local organizing committee, I would like to welcome all of you to the fourth conference on statistics and data science in a virtual format. We believe that this meeting will provide the exchange of knowledge between us, and that represents an advance in statistics and data science locally, nationally, and internationally. Locally, we have an extra motivation to organize this conference because our Department of Statistics has a very successful specialization in data science and big data, which filled in all vacancies with a long wait list. The third class is expected to start in next semester of 2026. Nationally and internationally, there has been a general movement on the statistics community towards the needs of data science, both in terms of research, education, and field of work. These topics will take place in the round tables of this conference, and outstanding researchers will share their expertise with us. The CSDS has become a reference event in statistics and data science worldwide, and the members of the organizing and scientific committee have been more motivated to prepare this conference each year. In the last few months, we have been working hard to provide you with a great scientific program that includes 6 great keynote speakers, 4 short courses, 2 roundtables, and contributed to posters. I hope you enjoy the fourth conference on statistics and data science, and that you'll be able to visit us in Salvador very soon. If you have any question or need any help, please contact me or one of the members of our team. Thank you all for being present and welcome to the first conference on statistics and data science.
And now, I would over to the Dean's Office for Research and Postgraduate Studies of the Federal University of Bahia on behalf of the Rector, Professor Olívia Maria Cordeiro de Oliveira.
Olá, bom dia a todos e a todas. Saudações a todos da mesa e a todos aqueles que nos assistem. Muitos parabéns a todos os organizadores do evento. Eu aqui represento o nosso magnífico reitor, professor Paulo César Miguel de Oliveira, o qual não pôde estar presente por estar em um outro evento agendado anteriormente, o qual não podia ter uma representação. Mas ele me pediu que externasse aqui a imensa satisfação pelo evento, denotando a nossa competência institucional, mais especificamente do Departamento de Estatística do Instituto de Matemática e Estatística da UFBA. E observando aqui os objetivos do evento, né, e agora falo como coordenadora de pesquisa da Pró-Reitoria de Pesquisa e Pós-Graduação, promover a colaboração entre vários grupos de pesquisa da UFBA, estreitar vínculos com empresas, impulsionar a especialização em ciência de dados, são objetivos, eu digo que multidisciplinares também e certeiros para a nossa alta produtividade técnica e científica. Bem, então, em nome do magnífico reitor, professor Paulo César Miguel, eu desejo um excelente evento para todos e muito sucesso. Muito obrigada.
And now, I word over to the head of the Department of Statistics of the Federal University of Bahia and chair of the Scientific Program Committee of the CSDS 2022, Professor Paulo Canas Rodrigues.
Good morning, everyone. Good afternoon or good evening, depending on the place you are right now. Initially, I would like to greet my colleagues in the opening table, Professor Alexandra Fábio, the chair of the local organizing committee, Professor Evandro dos Santos, Dean of the Institute of Mathematics and Statistics of the Federal University of Bahia, and Professor Olívia Maria Cordeiro de Oliveira, Research Coordinator of the Dean's Office for Research and Postgraduate Studies of the Federal University of Bahia, on the behalf of the Rector. I also greet the keynote and invited speakers, the short course presenters, the poster presenters, and of course, all the participants. Today, I'm here as the chair of the Scientific Program Committee of the 4th Conference on Statistics and Data Science, and also as the head of the Department of Statistics of the Federal University of Bahia. On the behalf of the Scientific Program Committee, I'm pleased to welcome you to CSDS 2022. This is the 4th edition of a very successful conference on statistics and data science that we have the pleasure to organize in the beautiful city of Salvador, this time in a virtual format. The organization of this meeting has been carried out in collaboration with the Department of Statistics of the Federal University of Bahia. At the Department of Statistics, we are quickly adapting to the data science movement and taking the lead in a field that we consider ours. For instance, in 2019, we created the specialization in data science and big data, whose second class will graduate in the end of this conference. Of course, you are welcome to visit the website. You can see there the posters and the videos of these students that are now finishing the second class. This has been a great success. Also, 2 months ago, we submitted a proposal for a master and PhD program in statistics and data science. We are very hopefully that this proposal will be approved. If so, it will be the first PhD on data science in Brazil. In addition, we are also in the process of writing and submitting a proposal for an undergraduate degree in data science. And we are also hosting, since the first edition, this very important conference on statistics and data science, which have become a national and international reference in the field. These are just a few examples of the efforts of the Department of Statistics of the Federal University of Bahia to lead and adapt to the area of data science. The purpose of this conference is to bring together researchers and practitioners from academia and also from industry. The idea is to develop and apply statistical and computational methods for data science. The main idea of this conference, it is a bit more difficult because it is in a virtual format, but the main idea is to provide a forum to share and discuss ways to improve the access to knowledge and to promote interdisciplinary collaborations. The scientific program, as it was mentioned before, it includes 3 keynote speakers, which are national and international references in the field of data science. We have 4 short courses, 2 roundtables, 1 invite paper session, 3 speakers, 1 general poster session with almost 100 posters, and 1 poster session where the students of the specialization in data science and big data will present their final projects. So this is a total of more than 130 contributions. The CSDS 2022 will offer opportunities to meet each other, to share scientific and professional experiences, and to promote new collaborations. The meeting will cover many of the research areas of statistics and data science. We also have an award for students or younger researchers. They could apply for the best poster award, and the winners will be announced at the closing ceremony. So don't miss that part of the conference as well. Although they were already listed by João, I would like to thank all institutions that have provided financial support or endorsement to this organization. We'd like to thank the Department of Statistics of the Federal University of Bahia, the specialization in data science and big data, the Brazilian region of the International Biometric Society, the CONRE 3, the American Statistical Association, the Brazilian Statistical Association, the International Society for Business and Industrial Statistics, the Special Interest Group on Data Science from the International Statistical Institute, to the International Association for Statistical Computing, and to the International Statistical Institute. As you can see in this list, there are the largest and most important statistical associations worldwide. ISI, the International Statistical Institute, and the American Statistical Association are probably the 2 largest and most international associations in statistics. So this is the reason why this is a very important meeting. Last but not least, I'd like to thank the keynote speakers, the lecturers of the short courses, the discussants in the round tables, the poster presenters. All of them have provided a great scientific program. Their contributions will make that happen. Thank you all for being here. And to all of you attendees, we would like to say that you are the main purpose of this meeting. We are honored by the presence of all of you and welcome you with open arms. All the work of the local organizing committee and scientific program committee was and is in the sense of offering you an adequate space for the presentation of your research results and also a place to interact and exchange experiences. We hope that your expectations are met. If there was any failure, please know that it was involuntary. I would like to conclude my speech by welcoming everyone with best wishes for an excellent 4th conference on statistics and data science. I hope that next year we can meet personally. Thank you.
And now we'll have the pleasure to listen to one well-known song of Bahia, performed by the singer Raíza Soares.
Raíssa Soares, and today I am accompanying Leandro Oliveira on the guitar. I am now going to sing a very special song from our Brazilian state of Bahia, related with the Carnival in Salvador, one of the great wind parks in the world. Its name is Raiz de Todo Bem. Salvador, Bahia, território africano, baiano sou eu, é você, somos nós, uma voz, um tambor. Oh, gente, cê não tá vendo que a gente é nordeste, cabra da peste. Sai daí, batucador, quem foi seu mestre? Capoeira, se plante, lá vem rasteira, é de ladeira. Preciso da fé do Senhor do Bom Fim, pra mim, pra você e pra mim. Um chinelo de couro, uma bata, uma benção, mais 50 centavos de som. Aumenta o som. África, ioiô, Salvador, meu amor, raiz de todo bem, de tanta fé, eu canto candomblé. África, ioiô, Salvador, meu amor, raiz de todo bem, de tanta fé, eu canto candomblé. Salvador, Bahia.
Thank you very much, Raíssa Soares. At this moment, we are concluding this session. We are grateful to the members of the opening table. And now we're going to have a quick break of 1 minute, and we'll have the opening lecture by Professor Alexandra and Schmidt. And when we'll be back, I will present the chair in the session, Lisandra Fabio and Paulo Canas Rodrigues. Now we'll be starting a quick break of 1 minute. Stay with us. It's only the start of the event. It's going to be great. Thank you. Hello, everyone. Welcome back. As we navigate through this quick break, I think we're going to watch a little video right now, right, Paulo?
I think we can start right away. We
can start right away?
Yeah.
Okay, that's okay. So at this moment, we're grateful to all of you that are watching our conference right now. It was made with great care. And now we invite you all to the opening lecture by Professor Alexandra M. Schmidt. And to present and chair this session of the honorable speaker, I would like to invite Professor Alexandra Fábio and Professor Paulo Canas Rodrigues. The floor is now yours.
Good morning, Paulo.
Good morning, Lisandra.
Good morning, everyone. Welcome to the fourth conference on statistics and data science. We're very happy to have you here today.
Welcome again to the CSDS 2022. Thank you all for attending this conference. I'm sure that you will not regret it.
Yes, this conference was prepared with a great care for you. A special scientific program was prepared to present you in these 3 days. We really hope that you all enjoy it.
We will have remarkable researchers and scientists that have been invited to bring us a lot of knowledge on statistics and data science. And now, to start the conference, we would like to introduce our first keynote speaker, Professor Alexandra Schmidt. She is Professor of Statistics at McGill University in Canada. Alexandra, is always a pleasure to see you, and thank you again for accepting our invitation. Alexandra is going to speak about coupled Markov switching count models for monitoring the spread of infection diseases. And I would like to introduce Alexandra. Alexandra, she is a professor of biostatistics and holds the endowed university chair in the Department of Epidemiology, Biostatistics and Occupational Health at McGill University in Canada. Currently, she is the program director of the Biostatistics Graduate Program. She's an elect fellow of the American Statistical Association, and actually, Alexandra is here on the behalf also of the American Statistical Association, and an elect member of the International Statistical Institute. She was awarded the Distinguished Achievement Medal in 2017 from the American Statistical Association, and she was in 2015. She was the president of the International Society for Bayesian Analysis. She's a member of the Environmental Epidemiology Research Group of EBOH, of the Quantitative Life Science Program, and associate member of the Department of Mathematics and Statistics. Her main areas of research are now on modeling of spatial and spatial temporal processes under the Bayesian framework. She was the chair of the local organizing committee, also of the 2022 ISBA World Meeting. This is the main meeting organized by the International Society for Bayesian Analysis, which was held in Montreal in Canada. Alexandra, thank you very much again for your availability, for being here today with us. And now the floor is yours, please.
Paulo, Lisandra, everyone, good morning. It's a great pleasure for me to be here. I'm speaking from snowy Montreal. It's a bit cold, a bit different from the beautiful video we just watched in Salvador. So I'm going to, I hope you can see my screen. Can you see my PDF?
We can.
Yes.
We can.
Perfect. Okay. So it's my pleasure to talk about this work. This is joint work with Dirk Dolz-Schultz. Dirk is a fourth-year PhD student here at McGill. And let me just try and move these, okay?
And he has been working on modeling infectious diseases, and in particular using coupled Markov switching count models. So I will try to divide this talk in two projects that Dirk has been involved with. Let's see, it's quite a bit of material. I'm assuming that I have about 45 minutes to give the talk. So let's see how this will work. So the first part of the talk is based on this paper that we published in Series C this year, which is on state coupled Markov switching count models for spatial temporal infectious diseases spread. Usually when we observe counts of infectious diseases, let's think about dengue fever across the neighborhoods of Rio de Janeiro. Here we have monthly data from 2011 to 2017 from two different neighborhoods. So clearly we see some seasonal pattern at the time series, but we also see a long string of zeros. And here, although they look like zeros, these are the actual zeros. So you might ask yourself, are these zeros true zeros? Do they mean that the disease is absent, or just that the cases were not reported? So one of the also, there might be, if you think about the evolution of the disease across time in each of the neighborhoods. So here we have maps of Rio de Janeiro divided by its neighborhoods. You can think about the event reemergence when the disease was absent at time t-1 and it becomes present at time t, or you can think about persistence when the disease was present at time t-1 and it's still present at time t. If we look at a simple exploratory analysis looking at this proportion of these changes of proportion of reemergence and persistence, we see that the patterns are quite different, the overall pattern across the space. So these motivated Dirk to think about a model that accounts for zero inflation in the counts, but also allows for different patterns of reemergence and persistence. So this is what I'm going to talk about first. So basically, usually counts of zeros happen quite often, and they can be handled with zero inflated models as proposed in 1992 by Lambert. The existing ZIP models, they only model the probability of overall disease presence. In a spatial temporal setting, we can separate, as I have just showed you on the maps, the presence of a disease in two events, which is the persistence, moving from presence to presence, or reemergence, moving from absence to presence. And infectious disease will often switch between long periods of presence and long periods of absence. And the usual ZIP model cannot handle these scenarios. And also the inclusion of random effects in the usual Bernoulli process of a ZIP model can lead to issues in sampling from the posterior distribution if you are a Bayesian, because it becomes close to improperty. And Markov switching models that switch between a zero state and a count state were considered in a temporal setting by Wang and in a spatial temporal setting by Malishkina and Mannering. And our goal is to extend their work. And throughout the talk, I'm going to show you how we are extending their work. So to set some basic notation, let YIT be the number of counts of a disease in area I and time t. And we are going to assume that YIT given a latent space. So we assume that there is a latent space which indicates presence and absence. So ST equals 1 is presence, ST equals 0 is absence. So if YT given ST equals 0, the disease is absent. Given as ST equals 1, we follow, the counts follow a negative binomial distribution with mean lambda IT and over dispersion parameter RIT, such that the variance is given by this formula here. So SIT is a binary indicator for the true presence, okay? But when we observe YT equals 0, we don't know if the disease is actually absent, right? It just means that we didn't observe any cases. It might be possible that the disease is present, but it was not registered. And back in 2009 with Marcos Fernandes, we developed a model that we made the SIT partially observed, in the sense that when we observed counts that were greater than 0, then we knew the disease was present. But when we observed zeros, we made the SITs unknown, and we estimated from the model. So we are building on this work by allowing this now that the probability of SIT being at a given state at time t-1 can change from absence or to presence. So basically, we can move from the disease being absent to present at time t, and we denote P01 as the probability of disease reemergence, or the disease might be present at time t-1 and it's still present at time t, and we call this event the probability of disease persistence. So this is the novelty of this model. One of the novelties, well, in comparison to Fernandez and others in 2009, that we allow this, we have these underlying states of presence and absence, and we can compute the probability of reemergence and persistence. So now I'm going to describe in more detail how we model these probabilities. This is the key, I would say this is the key contribution of this work, is how we model these probabilities here. So basically we write the logit of these probabilities as an overall intercept, the effect of covariates, and then we have this component here, which is a coupling parameter that represents the effect that the disease is spreading from neighboring areas has on the reemergence of the disease in area I and time t. And then we have a similar structure for the probability of persistence, but with different parameters. So if you go back here, what is changing is just the parameters here, that they are different, but the structure is quite similar. Okay, so basically the next question now is, how do we model these coefficients? How do we model these coefficients that are inducing the coupling and the communication between the states in different neighborhoods? So basically we have an overall intercept and the effect of covariates. And the covariates that we could think of are related to area, for example, the prevalence in neighboring area. We believe that if the prevalence is high in neighboring area, this will affect the probability of reemergence of the disease, right? And we could have also a gravid term, which translates the fact that individuals tend to move, they are more likely to move between bigger areas, more populated areas, okay? So the other part of the model is the modeling of the mean of the negative binomial distribution. In other words, of the positive counts. And we basically follow the endemic-epidemic model proposed by Bauer and Wakefield in this Series C paper in 2018, where we decompose the mean of the negative binomial as an effect of an autoregressive component. So it's meant to represent the transmission intensity of dengue in district I during month T, and an endemic risk that accounts for incidence that is not due to within area transmission. And basically, I'm a Bayesian. As Paulo mentioned on the beginning, I have already worked quite a bit for the International Society for Bayesian Analysis, and inference procedure, we will follow the Bayesian paradigm. So basically, this is the likelihood function of the model that I have just described. And the point is that the parameter vector that we have to estimate also includes the states, right? Because as I told you, they are partially observed. When we observe counts that are greater than 0, we know the disease is present, therefore SIT equals 1. But when we observe zeros, SIT is unknown, and we estimate this from the model. And I will not get into details about the inference procedure per se, but Dirk had to work on an efficient algorithm to sample from the resultant posterior distribution. Why is that? Because the states naturally impose a correlation structure in time, right? Especially because of that coupling component. We have unknown components also on the right-hand side of the equations of the logit probabilities of persistence and reemergence. So Dirk wrote customer samplers in Nimble, and inference is reasonably efficient. And I will show you at the end of the talk the address from which you can download the codes that were used to fit the models that we discuss in this paper. So basically for this data set, so we are looking at cases of dengue fever, monthly cases of dengue fever across the districts of Rio de Janeiro in Brazil. We fitted 3 different models. A model with no zero inflation, it's just the epidemic component, just the negative binomial. It doesn't account for the great presence of zeros on the data. A nested zip model, I forgot to mention, and I apologize for that the usual zero inflated model is a particular case of our model. We just have to set these coefficients to 0, and then zeta 0 has to be equal to eta 0. If this happens, we are back to the usual zero inflated model. So that's why we wanted to fit this model as well, to check how much better our proposed model performs in comparison to these other 2. So for the negative binomial component of the model, we modeled this lambda IT, the autoregressive component, so it's just describing the effect of previous cases as a function of rain and temperature. Why is that? Well, it's well known that environmental processes like rainfall, temperature, affects the life cycle of the mosquito that transmits dengue, right, Aedes aegypti. And we don't have information about the population of mosquitoes, unfortunately. So rainfall and temperature work as a surrogate to account for this relationship with the life cycle of the mosquito. As there is a delay, because a mosquito to be infected must bite a person who is infected, get infected, there is a whole process, so we used a 1 month lag of rainfall and temperature. The endemic part, we allow the intercepts at each neighborhood to change, and we assume a priori independent normal distributions with a common intercept. And for the endemic part, we have just an intercept that is centered on a common beta naught, and a variance that is measuring the variability among these components. What about the Markov switching component of the model? So the probability of the logit of the probability of reemergence is described in this fashion, and the logit of the probability of persistence is described in this fashion. But actually, I didn't update. I apologize for that, because we used the coupled models that had this structure here. I'm just realizing that I haven't updated. So we have these variables here in this in the modeling, capturing the coupling, the influence of the neighboring locations. So let me show you some results. So NP here stands for the neighboring prevalence, which is the log of this ratio. G stands for the gravity term. LC stands for local cases, and NN for number of neighbors. So basically what we have here is the WAIC. The WAIC is a model comparison criterion that one accounts for the posterior uncertainty, and also it has a component that penalizes for model complexity. The smaller, the better. And we clearly see that the model with endemic, epidemic only, that doesn't account for the zero inflation, performs much worse than the others. The model that has the usual zero inflated structure, it also performs worse than our proposal distribution, our proposed model. And here you have our model, but instead of having a negative binomial for the counts when the disease is present, we have a Poisson, and we see that the Poisson performs worse, suggesting that we needed that extra the over-dispersion parameter from the negative binomial to account for extra over-dispersion. But what we see here is that the model that tends to perform better, you will say, oh, but this is not the one with the smallest. Well, what we did, we decided for a compromise between model complexity and model fitting, and we decided to stop as soon as we didn't see a difference of 10 units in WAIC between the models. That's why we chose this one, because whenever you include covariates in the coupling component of the model, the inference becomes much more complex. So the results I'm going to show you are based on this model that has in the coupling component of the logit of the probability of reemergence, the neighboring prevalence, and also the gravity term. And if we look at the posterior summaries of the coefficients that go in the equations of the probability of reemergence and probability of persistence, here the first row is showing the probability, the estimated probability given average profiles of the covariates. We see that once the disease is present, the probability that it will persist is quite high, and population seems to increase. The greater the population of a neighborhood, the odds of reemergence increases by 6%. HDI, interestingly, was not an important variable because 0 is within the 95% credible interval. We see clearly the temperature, 1 month delayed temperature is associated, the increases. So if you increase temperature, the odds of reemergence, it's 24 times increases by 24%, and the persistence by 21%. But what is really what calls our attention is this number here, which is associated with the persistence. We see that previous cases, if the neighborhood had the presence and high cases, the odds of persistence are like at 5 times greater, okay? So these are, and clearly one of the messages from this table is that, yes, we needed different coefficients for the different variables, although we had the same covariates on the logit, on the models for the logit of probability of reemergence and persistence, we see that they are quite different. Here's just to show you, just to translate these estimates here and visualize, if you look at here on the y-axis, what you have is the odds ratio of dengue reemergence, given that the disease is spread from a neighboring area, and we see how it increases depending on the population of the neighboring area and the reported cases in neighboring area. And we see that the odds can increase quite a bit by how much, depending on how much the reported cases are or the population size of neighboring areas is. Here we have the posterior summaries of the parameters that go in the mean of the negative binomial distribution. And again, we see that rainfall and temperature have a positive association with the log of the mean. And we see that the overall intercept, the endemic overall intercept, the overall intercept of the endemic part of the mean of the negative binomial is around 0.37, and the over dispersion is relatively big as well. One of the summaries that we can provide, given a neighborhood if we think about average profile of a neighborhood. So let's think about a small district that the population is around 10,000 people, and we assumed average monthly temperature and rainfall values, and 2 cases reported in the previous months. This is the estimate posterior mean that we get for the probability of persistence in a neighborhood that has this profile of the variables. And this is the profile that we get of probability reemergence. What do we see? If we look at the y-axis, we see that the probability of persistence is quite high. And clearly in the winter months in Rio, between June and September, the probabilities decrease. But we see that once the neighborhood has the presence of the disease, the probability of persistence is quite high, right? And another interesting quantity that we can provide is this map for decision makers that we think that it's quite interesting. Basically, we have the map of Rio de Janeiro here, and the gray areas, they had reported cases, so we know the disease is present. The colored, the red shaded areas, they show the probability that dengue is present. So basically, it's showing the odds of moving from persistence being greater than 20% with a posterior probability of 0.75. And we can even indicate which the arrows are indicating these, right? Which neighborhoods are influencing the probability of the neighborhoods. So we find that this is an interesting summary for decision makers, because we can pinpoint regions that are more likely to have the presence of the disease. We are able to provide the panels here, they are showing, so I have 4 neighborhoods. Each neighborhood, we have the one step ahead fitted value and the probability of presence. So the solid circles here are the 1s and 0s, but the solid lines here are describing our probability of presence. And here you have the fitted value. So we see that, the fitted one ahead forecast. And we see that we are performing quite well, and the model adapts well to presence and absence. We also performed predictions. So we stopped in December 2017, I believe, and then we predict the number of cases for each of the districts and the probability of presence for the next 12 months. And we see that we perform reasonably well. So in summary, this first work, we proposed a zero-state coupled Markov switching negative binomial for general spatial temporal infectious disease counts. The usual zip model is a particular case of our proposal. The main difference with the existing models is that the disease switches between periods of presence and absence in each area through a series of non-homogeneous Markov chains that are coupled between neighboring locations. We model the reemergence of the disease separately from the persistence, and we can investigate whether a risk factor might affect the 2 events differently. We model the probability of having a consecutive zero state separately from the probability of having a consecutive count state. We can accommodate long periods of disease absence in conjunction with long periods of disease presence, which are often observed in small areas. And we consider spatial temporal correlations in the presence of the disease without using random effects in the Bernoulli process, which the literature suggests that might be a problem. You might have identifiability issues when you include these random effects. We account for the spatial structure by having this coupling on the states, right, of presence and absence. So this was the first part of the talk that I have. I hope I didn't go too fast. I tend to speak a bit too fast. But the next part of the talk is about a current project that Doug is developing. And this project was brought to us by David Buckridge. David is a professor in my department as well. He's an epidemiologist. And during the COVID pandemic, he was quite involved, he still is, with the Quebec province, with the province of Quebec in analyzing the data, making predictions, so on and so forth. And one of the problems that they had was to predict the surge of an outbreak, right? A new outbreak. So it's important for decision makers to know if there is a new outbreak starting, because you want to prepare the hospitals, right? It's likely that hospitalizations will increase. So this is an important problem. And Doug came up with a 3-state coupled Markov switching model. And this is what I'm going to talk about now. So unfortunately, Quebec has been the epicenter of the COVID epidemic in Canada. We had nearly 16,000 deaths and nearly 53,000 hospitalizations until May 2022. There was an immense strain that was placed on Quebec's hospital system. Actually, the system is still overwhelmed, is still suffering, but and many elective surgeries have been delayed or canceled, and there have been concerning shortages of essential medical supplies, drugs, and staff. What are the data? What is the data that we have available? Well, we have available weekly COVID-19 hospitalizations in the 30 largest hospitals in Quebec. Okay, I'm showing you the time series for 2 hospitals here, one in Trois-Rivières and one in Châteauguay. And so you see in the time series, for example, depending, this is a small hospital, this is a relatively small hospital that has 250 beds, and we see a sequence of zeros here as well. And you might ask yourself, these periods, these peaks that we see here, are they outbreaks? And when you go down here, are these endemic periods? Is this another outbreak? And what about these zeros here? Does it mean that there is an absence of COVID hospitalizations and this is an endemic period? Should we differentiate this period here with very low counts with these 0 counts? So our goal is to quantify how certain factors such as mobility and the introduction of new variants are associated with the emergence and persistence of the outbreaks. And we also would like to detect and forecast the outbreaks, okay? So basically, well, there are several challenges to modeling spatial-temporal outbreak occurrence. The exact start and end times of the outbreaks are not observable, right? When you see this peak here, this is already a peak, but maybe this has started earlier on. The same applies here. So we don't know the start and end times. The probabilities of outbreak emergence and persistence depend on several factors. The disease may go frequently extinct in some smaller areas, right? And it's expected that outbreaks will spread between areas. So existing endemic outbreak Markov switching models can adequately address challenges 1 and 2, but not 3 or 4. And this is what we are trying to accommodate with this proposal that Dirk is developing on his PhD thesis, as part of his PhD thesis. So going back to the time series again, we see this long string of zeros here. And one of the questions that Dirk had was maybe instead of having just 2 states, endemic and outbreak, maybe we should include a 3rd state, an absent state, to differentiate absence from endemic. And this absent state would only accommodate the zeros that we observe. Why is that? Because when we have these long periods of zeros, if they are embedded in the endemic state, then the mean of the process at the endemic state will tend to be smaller. It will be pulled down towards 0 because of the long string of zeros that we have here. So it might be a good idea to differentiate and have 3 states: absent, endemic, and an outbreak state. Okay, and this is what Dirk is proposing. So thinking about the outbreak spread, individuals will mix with those from other areas causing outbreaks to spread geographically, sometimes called traveling waves. So an outbreak should be more likely to emerge or persist in an area if there are outbreaks likely occurring in neighboring areas. So we would like to accommodate these. One way to achieve this is to use a coupled Markov switching model in the same spirit of the one that I have just showed you that was used in the zero-inflated negative binomial model. That coupled Markov switching model was to accommodate different states in the zero inflation component, right? Persistence and reemergence. Now here the problem is a little bit different. It's a bit more complex. We will let YIT be an epidemiological count indicator, for example, the number of hospitalizations due to COVID-19 at time T and hospital I. And we are going to have 3 states. State 1 indicates the disease is absent in area I and time T. State 2, the disease is endemic state. And state 3, there is an outbreak. Okay, the disease is an outbreak state. And we let NE of I be the set of all neighboring areas of area I. There are 2 different ways to describe the model. We can think maybe if it's easier to visualize in this way, suppose that you are at time T minus 1 and you are at area I and you have the neighboring areas. So we can think of the absence of the disease. So when there is absence, we observe 0 counts. okay? So the absence state will handle all the zeros in the time series. We have the endemic state, so when SIT-1 is 2, and we will model the endemic state as following a negative binomial with its own mean and its own over-dispersion parameter. And you have an outbreak state. The outbreak state also follows a negative binomial, but with different mean and over-dispersion parameter when compared to the endemic state. And you can move from these states. If the disease is absent, you can go to an endemic state. And we do not allow to move from absent to outbreak, okay? And P12 will denote the probability of disease emergence. So it's when you move from absent to endemic. P21 is the probability of disease extinction. And also, we will not allow to move from outbreak to absent. It has to go to an endemic period before. P23 is the probability of outbreak emergence, and P33 is the probability of outbreak persistence. So you can visualize this through this kind of diagram, or you can follow the same notations I had before, that you have YIT being a random variable whose distribution conditional on the state. If the state, the current state is 1, is absent, then YIT is 0. If it's 2, then YIT is generated from a negative binomial with this mean and this over dispersion parameter. And if YIT is 3, we have this negative binomial distribution. And then you have the transition probability matrix from moving from one state to the other. So if the disease is absent, you can only move to an endemic state. You cannot move to an outbreak, which we think is reasonable, right? To have an outbreak, you have to be in an endemic period first. Then you have the outbreak, which you can move from endemic to outbreak, or you can persist and be and stay in the outbreak state. But here in the endemic period, when you are in the endemic period, you can even go absent, or you can go to the outbreak. So here, these probabilities have to be more carefully modeled, because you have P21 and P23, right? So now there are 3 possibilities here. Whereas the others, we assign zeros because we assume these are reasonable assumptions we are making. Okay, so again, the point now is how to model these probabilities and how to model the mean of these negative binomial distributions. Do you realize that we have like 2 negative binomial distributions that are being modeled jointly, depending on the state the hospital is at time t? And we have this for each hospital, okay? We have to make some constraints about these negative binomial distributions. Otherwise, we are unable to identify the parameters in the model, right? So what we do, we model the mean of the log of the mean of the negative binomial, again, as a function of covariates. We allow each of the endemic and outbreak means to have their own coefficients, but we impose some constraints. So we are allowing random intercepts for both the endemic negative binomial and the outbreak negative binomial. But we assume that at each hospital, the intercept at the endemic plus 0.1 is smaller than the outbreak one. And we also impose another constraint on the autoregressive component, right? Because this is capturing the autoregressive history of the hospital. We expect that the greater the hospitalizations at time t-1, this will affect the mean of the respective endemic and outbreak periods. But we impose a constraint. We say that the endemic plus 0.05, so this place with the increase we expect to see to determine that we are in an outbreak period. So this helps us to learn about the memory of the process, right? Because it's an autoregressive component. And we expect that during an outbreak period, rho OB will be much greater than, the rho endemic, okay? Then we have to model the probabilities in the transition probability matrix, right? And we follow similar ideas to the previous work we assume that the logit of the probability of disease emergence and persistence is a linear combination of covariates, and we have this weighted sum of outbreak occurrence in neighboring areas, because this allows outbreaks to spread between areas, right? And the weight JIs, they are weights, they are known weights, okay? We fix these weights here. And for the probabilities of disease extinction and outbreak emergence, we have to be careful. As I said, this is, we have basically 3 probabilities to estimate here, but with the constraint that they sum to 1. So basically we follow a multinomial logistic regression that we model the probability of disease extinction or outbreak emergence with respect to staying at the outbreak state. And again, we follow similar ideas as these ones here, but with different coefficients. They are not the same. I made a mistake here. No, actually no, because the indices are changing here. So all these coefficients are changing. We are allowing the data to drive the inference and tell us if there is difference between these probabilities, right? As I said, different from the previous work, actually, I think I haven't mentioned this yet, but it's implicit. The states are unknown. Different in the previous work, we had partially observed the states, right? When it had counts greater than 0, S1 was always 1. Disease was present. But here we don't know. We don't know if we are in an endemic or outbreak period, right? So we decided to be able to identify the parameters in the model and perform the inference. We use the idea of clone states. The idea is that we impose the constraint that there will be a minimum endemic duration of 2 weeks and a minimum outbreak duration of 4 weeks. So if you enter in the outbreak state, you will stay there for at least 4 weeks, which again is reasonable, right? Because it all depends on the number of cases tend to increase, and we thought this is reasonable. And this helps us to prevent rapid switching between endemic and outbreak periods. Because before, when we didn't have these clone states, when we were looking at the fitted values and the probabilities of moving between states, we would see quite wiggly evolutions of the time series. We want to avoid that. So the clone states helps us to do that. Okay, again, inference is performed from a Bayesian point of view. Let me show you some results because I'm running out of time. So we fit the model to weekly COVID hospitalizations in the 3rd largest hospitals of Quebec between March 2020 and May 2022. We have available the number of beds in each hospital, the mobility, which Doc got from Google Mobility, and basically it's based only on retail and recreation. And it's lagged by 4 months, actually. It's not 4 weeks, sorry. So it's 1 month. It's lagged 4 weeks because, again, we expect there will be a delay, right, on people moving around, getting infected and being hospitalized. And the inclusion of a new variant. So it's 1 if 3 months after the introduction of Alpha and Omicron, and 0 otherwise, okay? And we include the new variant only for outbreak emergence, only in the modeling of outbreak emergence. We had weights, right? We had weights in the modeling when we are accounting for the outbreak state of neighboring hospitals. I told you that we fix these weights. How do we fix them? Well, we use the idea, we use the Bhattacharya distance, and the basic idea is that neighboring hospitals that are in an outbreak state will have greater weight. And we fit 3 models. We fit the model that we are proposing and 2 other models, one without neighboring outbreak indicators in the transition probability. So we remove this information about the outbreak indicator, and another one that has only 2 states, endemic and outbreak. This is to show you the difference and the advantage of fitting the model with an absent state, okay? if we look at, these are results that they have just come out. Dirk is currently finalizing the paper that we hope to submit soon. So what we see here on the first row are the probabilities of disease emergence, disease extinction, outbreak emergence, outbreak persistence. Again, we see that when there is an outbreak, the probability of persistence is reasonably high. And on the other rows, what we see are the relative odds ratios of the corresponding covariate. Okay, and the units are given in brackets here. So we see that the inclusion of a new variant really increases the odds of an outbreak emergence, and also the hospitals, the odds of disease extinction decrease by 56%. As the hospitals, as the population in the hospitals increase, and we also see that mobility increases the odds of outbreak emergence and outbreak persistence. Here we have the posterior summary of the parameters that go in the two negative binomial distributions. We see that the outbreak period has higher overall random intercept in comparison to the endemic one, and also the beds when we have an endemic period, we see that there is a positive association with the mean, the log mean of the negative binomial. I want to show you these plots. Basically, again, I have here two hospitals, okay, and the top one is showing the fitted value. So I have two. For each one, I have the pairs of plots. Here are the negative binomial distributions in red for the outbreak period, and in blue, the endemic period. And here we have the probabilities of the states. In blue, the endemic, in red, the outbreak, and in green, the absent period. And then on the bottom, we have a similar plot, but now assuming that we have only the endemic and the outbreak states. And we want to show you the difference, because I don't know if you can see, when we have the three states, we see that the mean of the endemic negative binomial accommodates well these observations here, whereas here they tend to be pulled down towards zero, because this long string of zeros is pulling down the mean of the negative binomial. So, and also when we have the absent state present, the change between states is smoother. So here it's changing between endemic and outbreak in a quite abrupt way, whereas here it's much better and suggesting that actually this is an endemic period. Okay. So this is just to show you why we believe it's a good idea to have these three different states. We can also perform real-time prediction. So we fit the full coupled and non-coupled models up to 6 weeks before, and then Dirk fitted the model including 1 week at a time and predicting. So he fits up to time 8-4 and then predict for the next week, then fit again, so on and so forth. And these are the predictions that we get. I don't have time to go through these plots. I think I will conclude. I just want to show you this map. For example, this is one map that we can provide that shows you the probability of being, so basically we have this is Quebec. The solid circles represent the hospitals. If you see red, it means that they are at an outbreak period. If you see black, we are uncertain. And how did we decide this? Looking, we say that it's red, it's outbreak. If the probability of being at an outbreak period is greater than 0.75, it's blue if it's greater than being in an endemic period is greater than 0.75, and it's absent if the probability is greater than 0.75. Okay, so we used the probability of 0.75 as the cutoff point to define if the hospital is in an outbreak or if we are uncertain. Okay, so just to summarize, we have proposed a 3-state coupled Markov switching model for spatial-temporal outbreak occurrence analysis. Unlike previous approaches, our model can account for periodic disease extinction in smaller areas and heterogeneous outbreak spread between areas through that coupled component. The analysis of COVID-19 outbreaks across Quebec based on admissions in the 30 largest hospitals showed us that mobility in retail and recreation venues, the introduction of new variants, and the occurrence of outbreaks in neighboring areas all had strong positive associations associations with the emergence or persistence of new COVID-19 outbreaks in Quebec. As for disease extinction and emergence, we only found evidence that the disease is more likely to go extinct in smaller areas. Disease extinction and emergence are rarer transitions, and so more data needs to be collected to study them with high precision. The addition of an absence state can be important in smaller areas for reducing bias in the endemic state distribution towards zero. Clone states tend to smooth out the state estimates, making them more realistic. In the real-time evaluation, we found that the incorporation of outbreak spread led to an earlier warning of the Omicron wave in Quebec, as the wave was highly synchronized across the hospitals. So I would like to end by thanking Ron Wasserstein and Paulo Rodrigues for the invitation to be a keynote speaker here. It's an honor for me to be here today. I also would like to thank NSERC and Ivado for the financial support to develop this work. If you are interested on the codes Doug developed for the first project, they are available from his GitHub. And the first part of the talk was published in Series C, and the manuscript about the hospitalizations analysis will soon be available in our archive. Muito obrigada, and wish you a nice day. Thank you.
Thank you very much, Alexandra. It was a very nice talk. Thank you for your availability and for sharing some of your work with us.
Thank you again. Thank you, and congratulations. I know how challenging it is to organize such a nice meeting. Congratulations, and again, it's a great pleasure for me to be here this morning.
I'd like to say thank you too.
Thank you.
Such a great way to start our conference. It was great presentation. You have shined this event. You are an inspiration for us, Williams. Thanks so much.
Thank you. Thank you so much for your very kind words. And again, if you need to get in touch, if you need to exchange ideas, you have my email here. I don't know if you can see it, but you have my email. Please feel free to reach out. It's always a pleasure to share my experience with you. Thank you so much.
Thanks so much. And everyone, I hope you have enjoyed the Alexandra. Now we will be going to the first hub table. It's of the first of the event. See you there. See you. It's a little delay.